In this video, we're going to wrap up our general discussion of functions with an introduction to function algebra and function composition, a couple of different ways that we can combine functions together. So function algebra is really no different from the standard algebra we use to manipulate expressions and equations once we get past some initial issues with notation. Functions can be added, subtracted, multiplied, and divided as algebraic expressions using their function rules. We can also perform algebraic operations on functions expressed as ordered pairs, which we'll see in a minute. Once we combine two functions together, we essentially create a new function that shares commonalities with the original functions it came from. If we want to find the domain of our new function, we have to take into account what was and wasn't allowed before. The domain of each combined function is the intersection or the overlap of the domains of f of x and g of x, what we're thinking of as the original two functions we combined together. We also need to make sure that we exclude x values that make g of x equal to 0 for division if g of x is the function that becomes our denominator in this case. Remember, our two cases when domain becomes an issue are when there's a problem to divide by 0 and when there's a square root in the problem. We have to make sure that we aren't making the inside of the square root negative. So now we're going to try a few examples in which we combine functions to find specific function values using functions written as rules and as ordered pairs. In both of these cases, the solution to each problem will be an actual number. You can think of it as a y value or a function output. Then we're going to take a step back and look at all things in general. If we want to combine functions in general to create a function rule, and we'll find the new function's domain. So let's try one. So we want to find the function value, if possible, given the three functions m of x, n of x, and p of x as defined. So the first thing we want to find is m minus n of negative 2. So we're combining the functions m and n with the algebraic operation of subtraction. So it's easiest just to break this down into two separate pieces. So if we're taking m minus n of negative 2, that's the same way of saying m of negative 2 minus n of negative 2. So it's almost like taking the negative 2 and distributing it to the m and the n. That's essentially what we're doing. It's not technically distribution, but it ends up looking like it. And for our purposes, you can kind of think of it that way. So now what we're doing essentially is we're doing two function evaluation problems in one bigger problem. So we're taking m of negative 2 as an individual piece, and we're taking n of negative 2 as an individual piece, and then we're just going to combine those together using subtraction. So I have to use two function rules in this case, the rule for m and the rule for n. So the rule for m says take your input, multiply it by 4. And then the rule for n says take your input, subtract 3, and then take the absolute value. And then we're combining those two expressions using subtraction. So now it's really just an order of operations problem. We combine everything inside the absolute value. At this point, you can think of absolute value as kind of working like parentheses. That's where it fits into order of operation. Absolute value bars function like parentheses. We have a multiplication. So we combine each of those individually. We simplify the absolute value. The absolute value of negative 5 is positive 5. So negative 8 minus 5 is negative 13. So m minus n of negative 2, we distribute the negative 2 in a sense to each of the functions, combine using subtraction, and our final answer is negative 13. Let's try another one. So we've got the same function rules. We're just going to combine a different pair with a different operation. So this is m times p of 1. So we're applying m times p, whatever that is, to an input of 1. So just like before, you can kind of think of the input as distributing to each of the individual functions. So another way of saying m times p of 1 is m of 1 times p of 1. So we take each of the individual function expressions and then we simplify them and multiply them together separately. So now we're using the function rules for m and for p. So notice p in this case is a rational function. So we're going to have to be careful here. So m of 1, well, m says multiply by 4. So m of 1 is 4 times 1. And then p of 1 is 1 over 1 plus 1. So plugging in, we get something like this, and we're combining these two functions using multiplication based upon the original function algebra statement we had. So now we want to simplify each of these. 4 times 1 is 4, and then 1 over 1 plus 1 ends up being simplified to 1/2. We multiply these together, and our final answer is 2. Let's try just one more with the same function rules. So let's do a division. We want to do p divided by n of 3. So the 3 distributes to the p, it distributes to the n. So this is the same thing as evaluating p of 3 divided by n of 3. So again, p is our rational function, and then n is a function involving absolute value. So I use each of my function rules applied to the specific input of 3. So p of 3, we're taking a rational function again, plugging in 3, so 1 over 3 plus 1. And then n of 3 is absolute value of 3 minus 3. So simplify the numerator, simplify the denominator. The numerator is going to be 1/4. The denominator, we have 3 minus 3, well that's 0. Absolute value of 0 is 0. There's a problem here. This is undefined. 1/4 divided by 0 is undefined. Anything divided by 0 is undefined. So in this case, from the beginning, we can complete the algebra, but once we get to the end, we realize that the expression we have is actually undefined. Another way of saying this is that although 3 is contained in the domain for n of x and for p of x, it's not contained in the domain for p over n of x. Once we divide, having that n of 3 in the denominator becomes a problem because n of 3 is 0. So if we were to find the whole domain for p over n as a new function, 3 would be a value that's not included in that domain. Now let's try a couple where our functions are given as sets of ordered pairs. Remember, we can define a function with a rule, or we can define it with a set of ordered pairs or with a graph. So in this case, we have a set of ordered pairs. So we want to find two different algebraic combinations. First one is f plus g of 4. So another way of saying that is f of 4 plus g of 4. So we're evaluating each of those individual functions based on how f and g are defined. So first one, f of 4. I go to my rule for f, and I'm assuming the input is 4. So I'm looking for an x value of 4. So I have a single point in the definition for f where the input is 4. When the input is 4 for f, the output is -2. So f of 4 is going to be -2. Now for g, same thing. We go to the rule for g. We look for an input of 4 or an x value of 4. And the y value that goes with an input of 4 is going to be 3. So f of 4 again is going to be -2. G of 4 is going to be 3. And then I just combine and simplify. -2 plus 3 is going to be +1. Now let's try g times f of 0. So g of 0 times f of 0. We're distributing that 0 to each of them, combining with multiplication. G of 0, well, I go to my rule for g, look for 0, an input of 0, my output is 6, and then go to the rule for f. The input is 0, the output is 3. So g of 0 is 6, and then f of 0 is 3. Multiply those two together, and I get 18. So it's just as simple to use a rule or ordered pairs. Set of ordered pairs may be even a little faster, just because we're just matching up x and y values. We're not actually performing any really in-depth algebra. So we've done a few examples where we found an actual numeric value for some type of algebraically combined functions. Now we're going to take a step back and we're going to actually define a new function defined from an algebraic combination. So as opposed to doing something like f plus g of 4, now we want to know what is just f plus g of x. What if we just wanted to combine our functions in general and come up with a new rule that we could then apply to function inputs? Okay, so here's our first example. So we're going to do a combined function and we want to find its domain in interval notation given the three functions defined as g of x, h of x, and k of x. So here's what we want to find. We want to find g plus h of x. Now notice in this one it's of x, it's not of a specific number. So our answer is not going to be a specific number, it's going to be some algebraic expression that combines the two rules for g and for h. Now in terms of how we treat this, initially we treat it just the same as we did before. So you can kind of think of the x as distributing back to the g and to the h. So what we're really finding when we're finding g plus h of x is we're finding g of x and h of x, and we're combining them with addition. So I go and I determine my rules for g of x and for h of x. So g of x is a linear function, And then h of x is actually what we're going to call a quadratic function. Notice that x squared, that comes from the quadratic parent function. So h of x is a quadratic function. So I sub in my two rules. Remember, I don't have any actual numbers here, I just have x's. So all I can sub in here are going to be the rules for g of x and for h of x. Now it's just a matter of combining like terms. So I have one quadratic term, I have that x squared, and then I have two linear terms. I have a positive 2x plus a negative 4x. So if I combine those and then write them in order of exponents, I have x squared minus 2x. So that's going to be my final function. That's the combined function we get from g plus h of x. So we found our new function, we found our combined function. Now we want to find the domain for this new function. So when we're finding the domain for this function, we have to take into account the domains for the functions that this came from. So remember, this new function came from g of x and from h of x. So we have to take into account the kind of numbers we could plug into those two functions. Whatever the domain is for g of x and h of x, we take those and combine them together, and whatever values they have in common, that's going to be the domain for g plus of h of x. So the first thing we need to do is we need to find the domain of each of those individual constituent functions. So g of x is 2x. Remember, this is a linear function, so that's going to be a diagonal line. So as we mentioned before, whenever we're finding domain from a function rule, we're looking for exclusions. So we're assuming that our domain is all real numbers. We're assuming we can plug in anything we want. And then we just want to determine, is there anything from all real numbers that's going to give us a problem? The only two cases where we run into a problem are situations where we have a denominator and we could divide by 0, or if we have a square root and we could potentially make the number under the square root negative. Those are the only two cases we have so far where there's an issue with domain. So in this case, our function g of x is equal to 2x. It doesn't have a denominator, it doesn't have a square root, so neither of those cases apply. So that means our domain is going to be all real numbers. Now you're going to see in a minute that it may be helpful to have a graph of the domain so that we can compare the two domains for our combined functions. So I'm going to draw the graph of this domain on a number line. You can think of that number line as representing the x-axis. Remember, if we were to graph this function and we wanted to find the domain, we would just slide all the points onto the x-axis, and the range in the x-axis that's covered represents the domain. So it sometimes helps to draw a graph of the domain in order to compare the two domains. So our domain is all real numbers, so we cover the entire number line. Okay, so our other constituent function was h of x, which is equal to x squared minus 4x. We're in essentially the same situation, so there's no denominator, there's no way we could divide by 0, and there's no square root, so there's no way we could have a negative number under a square root. So without either of those cases, our domain is automatically all real numbers. So again, if we were to graph this, we cover the entire number line. So our final function was g plus h of x, and we decided that's equal to x squared minus 2x. So the domain for this function is going to be whatever the two original domains had in common. It's going to be the overlap of those two domains. Well, in this case, both domains are the same. So the overlap is the entire real number line. It's everything from negative infinity to infinity. There aren't any exclusions from either of them, so they have every single number in common. So because the overlap is all real numbers, that means the domain for our final function is also going to be all real numbers. Let's try another one. So we've got the same functions, but we're going to combine a different pair in a different way. So now we want to find g times k of x. So our of x part is distributing to our g, distributing to our k, so we're finding g of x times k of x. So we go to the rule for g, we go to the rule for k. We just combine those two rules together, this case using multiplication. Now we have parentheses around the 2x in order to separate it from everything else, and we have a dot in between to symbolize multiplication. But in this case, neither of those really mean anything. So we can drop the parentheses, we can drop the multiplication, and we still have an expression that means the same thing. Now there's no way we can simplify the square root. The 2x does not distribute into the square root. So this is essentially our final function in its simplest form. So g times k of x is equal to 2x times the square root of x minus 1. So let's look at the domain. Domain's going to be a little more interesting here because we know we have one function as a constituent function where there may be some problems. So we'll see that in just a second. So g of x equals 2x. We already decided the domain for this one was all real numbers. So if we graph it, we have the entire real number line from negative infinity to infinity. Our next function was k of x is equal to the square root of x minus 1. So once we have a square root, this is one of our potential issues with domain. Remember, we can't have anything negative under the square root. So we have to make sure that whatever x minus 1 is, it has to be greater than or equal to 0. So a quick way to figure out which side of the 0 number is going to be included is determine what value would give you 0. Well, in this case, if x were 1, 1 minus 1 is 0, so that's where we would have our 0 number. Okay, so now let's consider what happens on either side of x equals 1. If we pick a number bigger than 1, so say we pick 2, well, 2 minus 1, I don't care exactly what 2 minus 1 is, I just care that it's a positive number. So if I pick anything bigger than 1, I'm going to be putting positive numbers under my square root. I may not have pretty square roots, but at least I'll have something that I can take the square root of. I'll have a positive number on the square root. So if I pick anything bigger than 1, I'm generating positive numbers under my square root. Now what if I pick something less than 1? So let's say I pick x equals 0. So something less than 1, anything less than 1. 0 minus 1 is going to be negative 1. So now I'm trying to take the square root of negative 1. That is a problem. That's not defined on the real number line. That doesn't exist anywhere in the coordinate plane if we tried to graph it. So anything less than 1 is going to be a problem. So I can pick numbers greater than 1. I can't pick numbers less than 1 because they're going to make whatever's under the square root negative. So that means my domain for this function is going to be 1 to infinity, including 1. We can plug in 1. We can take the square root of 0. That's fine. But we can't have anything less than 1. So if we graph this on the number line, this is only a portion of the number line. This is only everything from 1 to infinity. So anything less than 1 is not going to be included as part of this domain. So our domain for our final function, for our algebraically combined function, is going to be the overlap of these two individual domains. Well, notice these two domains are not the same, so the overlap is not going to be the entire real number line. The overlap is going to be that portion from 1 to infinity. So notice that 1 to infinity is a part of all real numbers. It's if we plugged it into all real numbers and then added some, we would get all real numbers. So it's included in the range from negative infinity to infinity. So in this case, the overlap is 1 to infinity, including 1. So that means our domain for our final function is going to be that overlapping area, which in this case is 1 to infinity. So let's try just one more and then we'll move on. So again, same rules. Let's do a division this time though, because we know there's one extra thing we have to take into account with division. So now we're doing a division. So k over h, or k divided by h, of x. So that's going to be k of x divided by h of x. So I plug in my rule for k of x, I plug in my rule for h of x, and then there's nothing I can do to simplify this. This is as simple as it goes. Okay, so our final function is the square root of x minus 1 divided by x squared minus 4x. So this is a substantially more complicated function than the other two we ended up with before. So let's see what happens with the domain on this one. So we need the domain for each of our individual functions. We just found this one before, so k of x is equal to square root of x minus 1. The domain is going to be everything from 1 to infinity. Remember, we can't plug in anything less than 1 because that's going to make whatever's under the square root negative. So if we graph that, that's part of the real number line, just from 1 to infinity. Our other constituent function was h of x, which is equal to x squared minus 4x. There's no division here, there's no square roots, so our domain is all real numbers. It covers the entire real number line. And then our final function was k divided by h of x, which had a square root in the numerator, and then something quadratic in the denominator. Okay, so initially we say, well, we have the overlap. The overlap would be 1 to infinity, and then we're good. There's a problem here, though. There's our overlap, but we also have to take into account that the denominator cannot be 0. So yes, we are including the overlap. that's fine, but we have to make sure that because we now have a denominator as part of our final answer, that we don't pick any x values that will make the denominator 0. So we need to figure out what x values are going to make the denominator 0. So I'm going to take my denominator, I'm going to set it equal to 0, and then I want to solve for x. So to solve something like this, I need to factor. I'm looking for a greatest common factor in these two terms. So I notice that each of these terms has an x in common, so I'm going to factor out an x. And then I'm left with an x minus 4 from each of those terms. So once I have two factors and they're equal to 0, I set the individual factors equal to 0, and I would get x equals 0 and x equals 4. Well, notice that x equals 0 is not included in the overlap. The overlap is everything from 1 to infinity, so x equals 0 is already outside of that particular range of values. However, x equals 4 is included in that range of values. It's a little bit past 1, so it's included in the range from 1 to infinity. But because x equals 4 is one of the numbers we could plug in and make the denominator 0, we have to make sure we exclude it. So our final domain is going to be that overlapping region, that 1 to infinity range, minus that number x equals 4. So it's everything from 1 to 4, and then everything from 4 to infinity, just broken up around that number 4. This is how we write it. So we have everything from 1 to 4, including 1, but not including 4. So there's a bracket with 1, there's parentheses with 4, because there's a hole at 4. And then we can also include everything from 4 to infinity except 4. So again, we put parentheses around it. So it's the range from 1 to infinity just split up around that number 4. So this is just a general survey of the kind of problems you may see where you need to combine functions together. Keep in mind for every different function we have to take into account a different domain, and each time we combine functions in different ways we end up with new functions where we also have to take into account domain restrictions. Function composition is another operation we can use to combine two functions together. Function composition is using a function as the input for another function. In other words, instead of plugging in a number to our function, we're plugging in another function. This is a concept that's used a lot in calculus when we want to work with complicated functions and break them down into components, something plugged into something else. So we have a specific notation for function composition. The symbol looks a lot like the degree sign placed between the two function names. Reading it aloud, we say f composed g or f composed with g. But another way to think of it is f of g of x. So f of g of x. This particular way is very helpful because it helps us translate the statement into a more useful form. What we're doing when we compose f and g is we're taking g of x, the function that's in the middle, and we're plugging it into f of x, the function that's on the outside. So we determine what g of x is, then we're applying the function f of x to that. In other words, g of x is now becoming the specific input that goes into the input section for our function f of x. So keep in mind that we could just as easily evaluate g of f of x. The labels are completely arbitrary, so our actual composition depends on what we're told to find and the functions we're given. Just as with function algebra, what we get from function composition is a new function made up of the two original functions. So something we may need to do, again, is find the domain of the new function. When we want to find the domain of a composition, we have to take into account what is and isn't defined as any point in the problem where we could plug in a number in place of x. Specifically, the domain of a function composition takes into account restrictions for the inner function, in other words, the function we're plugging in, and the final function, what we would think of as the answer to the problem. So if we're finding f of g of x is our inner function. We need to make sure that when we're plugging g into f, that whatever is and isn't allowed as an input for g of x is taken into account. Once g of x is plugged into f of x and the whole expression is simplified, the structure of the problem may have changed. We may have new areas for concern with regards to domain. So we have to reevaluate at the very end what can and can't be plugged into our function. The actual final domain excludes any numbers that were problematic at either of these 2 points I just mentioned. So now we're going to do the same thing with function composition that we did with function algebra. We'll find a couple of compositions where we're plugging in numbers and getting a numeric answer, function rules and ordered pairs, and then we'll do a few general compositions where we're creating a new function and finding its domain. So let's try a couple with numbers. So we have the functions f of x is equal to x squared plus 2x and g of x is equal to x minus 4. So we have a quadratic function and we have a linear function. So first one we want to find is f compose g of 6, otherwise f of g of 6. So the way we read it is the way we write it, f of g of 6. So g of 6 is g with a 6 plugged in, and then f of that means we're plugging in g of 6 as the specific input for the function f. So as with order of operations, you start from the inside. So anywhere you have parentheses, you start there. So g of 6 is inside of the parentheses for f. So where we're going to start is with g of 6. So forget about f for a minute. Now we're just worried about g. So go to the rule for g. G says take my input and subtract 4. So g of 6 is the specific input of 6 minus 4. Now again, we haven't touched f, so f is still there. So now we have f of whatever g of 6 was equal to, and we decided that was going to be 6 minus 4. So we simplify down our input, 6 minus 4. That's now going to be f of 2. So g is completely gone from the problem now. Now it's just f and the input for f. And notice at this point that the input for f is different from the input of the original problem. That's not a coincidence. That's typically going to happen. So once we've evaluated the inner function, in this case g, with the input we were given, that's going to be a completely new number. So once we get to the outer function, we have a completely different input that we're now evaluating with. The input we're using is whatever g of 6 was equal to. In this case, it was equal to 2. So now I go to my rule for f. The rule says square my input, multiply it by 2, and then add those two things together. So it's going to be 2 squared plus 2 times 2. So simplify those down. It's going to be 4 plus 4, which is 8. So f compose g of 6, or f of g of 6, is going to be equal to 8. Let's try another one. So now we want to do g compose f of negative 3. So notice in this case the order has flipped. The order we plug functions in is based on the order it's written in the problem statement. So now f is considered to be the inner function and g is going to be the outer function. So g composed f of negative 3 is the same thing as saying g of f of negative 3, and that's how we write it, g of f of negative 3. So f of negative 3 is now being plugged into g. So we start on the inside, f of negative 3. So now we're using the rule for f first, and we're going to disregard g for a minute. We're just worried about what f of negative 3 is. So I go to my rule for f, we square, we multiply by 2, we add them together. So that's going to be g of whatever f of negative 3 is. So we simplify inside parentheses. That negative 3 squared is going to be a 9, and then 2 times negative 3 is negative 6. So g of 9 minus 6, otherwise known as g of 3. So again, notice that our current input now for the function g is completely different from the original input for the problem. Once we simplify f of negative 3, whatever that is, that now becomes the input for our external, for our outside function, which in this case was g. So I go to my rule for g. G says take your input, subtract 4, so 3 minus 4, and our answer is negative 1. So g composed f of negative 3 is equal to negative 1. Another thing I want you to keep in mind is that order is very important when we're doing a function composition. So say we did f of g of 6, we know that's going to be 8. If we did g of f of 6, we cannot assume that the answer is going to be 8. So if we change the order for composition, it typically will completely change the problem. It'll completely change the answer. So you can't assume that one and the other are going to be the same. That's actually going to make a difference here coming down the line, few sections. We're going to talk about the order for composition and why it matters, what a big deal that makes. So you have to keep in mind when a composition is written in a specific order, you have to abide by that order. Whatever's on the inside is going to be plugged into whatever is on the outside. Now let's do the same thing, but let's do it with ordered pairs. So we have two functions, and now they're defined as sets of ordered pairs instead of being defined in function notation with a rule. So we want to find g composed f of 2. So g of f of 2. So again, follow order of operations, start on the inside. We're starting with f of 2. So I go to my rule for f. I'm looking for an input of 2, so an x value of 2. So I have a single point, 2, 4, that has an input of 2. The output that goes with an input of 2 is going to be 4. So f of 2 is going to be 4. So this now becomes g of 4. Then I go to my rule for g. I'm looking for an input of 4, not an input of 2. Don't make that mistake. We're looking for an input of 4 now, not an input of 2. That 2 is completely gone. So I have the point 4, 3. My output for an input of 4 is going to be 3. So g of 4 is going to be 3. So g composed f of 2 is 3. Now let's try another one. So now we want to do f composed g, opposite order, of 5. So this is f of g of 5. That's what this means. So I go to my rule for g. I'm looking for an input of 5. So my output corresponding to an input of 5 is going to be 7. So now I'm looking for f of 7. G of 5 is equal to 7. So this is now f of 7. So then I go to my rule for f. I'm looking for an input of 7. Now I've only got 5 ordered pairs and I can't make any assumptions about anything else. These are the only ordered pairs that are part of the function. And what I'm noticing is I don't have a point with an input of 7. I don't have a point with an x coordinate of 7. So what do? What happens? Well, since there is no point in f corresponding to x equals 7, it means this composition is undefined. There is no answer. It's undefined. There is no solution for this one. So what this means, it means that if I were to define f composed g as a new function, 5, the original input, is not part of that function's domain. Although I can plug in a 5 to g, I can't plug in a 5 at the end once I've composed things together. So even though 5 works at first, it works for g, it doesn't work for the problem as a whole. So 5 would not be part of the domain for f composed g as a new function. So let's wrap it up by trying a few where we have functions in function notation with a rule, and we want to find a new function as opposed to finding a numeric output. So we want to find an actual rule defined for that particular composition, and then we're going to find the domain. So we've got f of x and g of x. G of x is a rational function. F of x is a linear function. We want to find f composed g and its domain. So f composed g, remember that means f of g of x. So g of x is on the inside. It's what we're plugging into f of x. Now, because we don't have a specific input, there aren't going to be any numbers necessarily in this problem in place of x. We're going to have x's. So all I can sub in is whatever g of x is equal to, which in this case is 1 over x plus 4. So that's now subbed in place of g of x. Now I'm going to star this spot. This is the first spot where I need to consider the issue of domain. As soon as I'm plugging something in, I need to consider what the issues may be with domain. And I'm already seeing that there may be an issue with domain here because what I plugged in has a denominator. And we know that anything with a denominator has a potential for divide by 0, which is undefined. So we're not going to worry about it at the moment, but we're just going to mark that spot so that we know we need to come back to it. That's one of the spots where we need to consider domain. So now g is completely gone. Everything is in terms of f. So we're finding f of 1 over x plus 4. So 1 over x plus 4 is now going to be the specific input for the rule of f. So the rule for f says take whatever input we're using, multiply it by 2, and subtract 6. It doesn't matter that we're plugging in something that has an x in it. We're going to take that input verbatim, and we're going to apply the operations in f to it. So we're multiplying the input by 2, and we're subtracting 6. So now it's just a matter of taking your algebra skills and simplifying this down. So the 2 needs to distribute. The 2 distributes to the top. So think of the 2 as a 2 over 1. So the 2 multiplies by the 1 in the numerator, and then it's just distributed over the denominator. So we have 2 over x minus 4 minus 6. Now our goal is to combine and have one rational expression as our final answer. So I can't combine that minus 6 without a denominator. I need a common denominator. In this case, there's only one denominator in the problem, so that's the one I want my 6 to have. So I'm going to multiply 6 on top and bottom by x plus 4 over x plus 4. So this way, I now have two rational expressions, and they each have the same denominator of x plus 4. So before I combine the numerators, let's simplify that second numerator. So the 6 distributes to the x, and it distributes to the 4. So we have 2 over x plus 4 minus 6x plus 24 over x plus 4, both of them over x plus 4. We're combining using subtraction. So be really careful here. Notice both terms in the second rational expression have to be subtracted. So you can think of that subtraction as kind of distributing. That's exactly what it's doing. It's distributing to the 6x and to the 24. So 2 minus 6x minus 24. So we have a negative 6x, and then 2 minus 24 is going to be negative 22. So our final answer is going to be negative 6x minus 22 over x plus 4. Now, if there is any simplification possible at this point, you want to continue to simplify. If there's a common factor in the numerator and denominator, you have to simplify it. You have to divide it out. You don't have a choice. In this case, there isn't anything in common. There's no way I could factor out anything that would cancel with the denominator, so this is going to be my final answer. And I'm also going to star this point, because this is another point where we have to factor in what the domain is. At the very end, the structure of the problem has changed, so we have to make sure that nothing has changed in terms of domain. Is there anything that we could plug in before that now we can't plug in? So we take into account domain as soon as we plug in the inner function, and then we also factor in domain at the very end once we have our final function. So the points we star, these are where we're going to check for domain restrictions. So we want to first find the domain of 1 over x plus 4. So we have a denominator. The denominator can't be 0. Well, the only thing that would make this denominator 0 is negative 4. Negative 4 plus 4 would give us 0. That's the only way we could have a 0 in the denominator. So our domain is all real numbers except negative 4. So it's all real numbers split up around that number negative 4. So that's our domain there for g of x for the inner function. Now we have to consider the domain for the final function once we've composed f and g together. And it turns out it's actually the same. The denominator hasn't changed. Now notice the numerator has changed, but the numerator doesn't matter. We can have a 0 in the numerator. That's completely legal. 0 divided by something is just 0. It's just when we're dividing by 0 that we run into an issue. So division by 0 is not defined. Division with a 0 in the numerator is just going to be equal to 0. So because the denominator is still the same, even though the numerator is different, we still have the same domain. So because these two individual points where we have to consider domain give us the same restriction, the only restriction is negative 4 is not included, the domain for our final answer is also going to be all real numbers except negative 4. So negative infinity to negative 4 to infinity, split up around that negative 4 union together. Now let's compose the same two functions in the opposite order. So we just did f compose g. Now let's do g compose f. So as I mentioned before, order matters. Typically, g of f and f of g are going to be two separate things. So g of f we expect to give us a different answer. So g composed f is g of f of x. So f of x is now going to be the input for g. So I don't have any specific input to plug in, it's just the generic input of x. So the only thing I can put in place of f of x is going to be the rule for f of x, which in this case is 2x minus 6. So now f is gone, it's entirely in terms of g. G was our rational function. So now I'm going to use this specific input of 2x minus 6, and that's going to be plugged into the algebraic operations for g of x. So g of x says take our input, add 4, and then take the reciprocal of that, so 1 over whatever that is. So again, this is a situation where I need to immediately consider domain. As soon as I plug in anything in place of a function, I have to make sure what I'm plugging in is defined. So this is our first point where we consider our domain issue. So we plug in our 2x minus 6, we add it into our g of x, and so now we have 1 over 2x minus 6 plus 4. So I combine my like terms. I can simplify in one step. The negative 6 and the plus 4 combine together. So we have 1 over 2x minus 2. And again, this is a rational function, so if we could simplify, if there's anything in common in the numerator and denominator, we want to simplify that for sure. In this case, there's nothing that could cancel with that 1 in the numerator, so we just leave it alone. This is our other spot where we have to consider domain. So fundamentally, the structure has changed. 2x minus 6 has now changed into 1 over 2x minus 2. So I need to consider domain for both of these points. So these points are we're going to consider the restrictions. For our first one, for 2x minus 6, there's no division, there's no square root, so our domain's going to be all real numbers. We can plug in anything we want, and it's defined at this point in the problem. For our final function, it turned into a rational function. It turned into 1 over 2x minus 2. So now we have to consider where we would divide by 0. Well, in order for our denominator to be 0, x would have to be 1. So 2 times 1 would be 2. 2 minus 2 is 0. So if x is 1, that would be the only value of x that makes us divide by 0. So notice in this case that we have two different domains for each of those individual points. So although the inner function has no restrictions, the final function does. So our actual domain for the problem has to include this restriction at the very end. So our final domain is negative infinity to 1 union 1 to infinity. So excluding that point at x equals 1 where we have an issue with the final function. So let's try one final composition. So now we have a rational function and a radical function. So if you can wrap your mind around this one, then you're solid. You've got it all. So we want to do specifically m composed p of x. So in that order, m composed p. So m of p of x, that's how we translate this. So p of x is our radical function. It's the one with the square root. So this is going to be m of square root of x minus 2. Okay, so we know this is our first spot where we need to check for domain, and we know there may be an issue with domain here because we have a square root. So we're going to have something other than all real numbers as our domain at this point in the problem. So p is gone. Now we're writing everything in terms of m. M is a rational function. So we're taking our function m and we're plugging in this specific input, square root of x minus 2. So we plug it into m. I have 1 over square root of x minus 2 quantity minus 5. And there's nothing else I can do to this. You may have been forced to rationalize in previous classes. In other words, if there's a square root in the denominator, you have to get it out of the denominator. There are techniques for doing that, but we're not too worried about that here. So you can just leave it in the form it's in. So our final answer is 1 over square root of x minus 2 minus 5. This is our final function, which means that we also need to consider any restrictions we'd have at this particular point. So let's check our domains. So for square root of x minus 2, we have to make sure that whatever's under the radical is positive. So if we were to plug in a 2, we'd have 2 minus 2, which is 0. We can take the square root of 0, we're good. If we pick anything greater than 2, we're taking the square root of a positive number, which is legal, it's defined. If we pick anything less than 2, we're now taking the square root of a negative, which is undefined. So we only want to keep the numbers that are going to be greater than or equal to 2. So our domain is going to be 2 to infinity for that original function we plugged in. Now what about the final function? So this final function is pretty complicated. It has that same square root. So we know that whatever restrictions we had on that square root, we still have here. But it also has a denominator. So we have to take into account two different things here. We have to take into account that we have that square root. We've already figured out what the restrictions are for that. But we also have to make sure that our denominator is not 0. So we know what makes our square root okay. We don't know officially yet what makes our denominator okay. So let's take our denominator, set it equal to 0. We need to see what value of x is going to make the denominator 0. So move your 5 over. We want to get the square root by itself so we can eliminate it. Add the 5 to both sides. Now, in order to get rid of a square root, the opposite of a square root is squaring. So we need to square both sides. So if we square both sides, we now have x minus 2 is equal to 25. I add 2 to both sides, and I'm left with a 27. So what is our domain going to be in this case? So we've got the square root. We know that whatever restrictions we had just for the square root, they still apply. So we have to make sure that we're only plugging things in that are greater than or equal to 2. However, because that square root's in the denominator and we have to make sure our denominator is not 0, we have to exclude the x value 27. We decided that's the value that would make our denominator 0. So we want everything from 2 to infinity except 27. So we're going to take that interval 2 to infinity and we're going to split it up around the number 27. So that becomes 2 to 27 union 27 to infinity split up around that number 27. So parentheses around 27 so it's not included. So again, the reason we had to do this, the square root has to be positive, so everything has to be greater than or equal to 2, but the denominator can't be 0, so x equals 27 is what makes the denominator 0. We have to exclude that. So that means our final domain is going to be 2 to 27 union 27 to infinity. To summarize, we can combine functions using algebraic operations, just the standard operations you learn: addition, subtraction, multiplication, and division. These are not the only algebraic operations you can perform on functions, but they consist of the basic 4 that pretty much everyone uses. So functions can be added, subtracted, multiplied, and divided using either their rules. In other words, if we're defining in function notation and we have a rule that tells you how to take an input and get an output, you can use the rule as an algebraic expression. Or if a function is written in terms of ordered pairs, you can also use the x and y coordinates from your ordered pairs to add, subtract, multiply, and divide. So the domain for a function combined using algebra is going to be the intersection of the original function's domains. So if you're combining two functions together, each of those individual functions has domain, potentially restrictions. When we take two functions and combine them together, the final domain has to take into account anything we excluded from the individual domains. So what those two original domains have in common, that's going to be the domain for our final answer. We can also combine functions using function composition. So the notation for function composition looks like a degree symbol between the two functions we're combining. Don't confuse that with multiplication. So an open circle is function composition. A closed dot represents multiplication. So function composition means plugging a function into another function. So in this case, whatever function's in the middle or on the right, you can think of it either way, that's going to be plugged into whatever function is on the left. The left-hand function is going to be the external function. So functions can be composed using rules. So using function notation, we define a rule to find an input from an output, or corresponding ordered pairs, just as before. And the domain for a function composition has to take into account restrictions for the inner function, as soon as we plug in this case, what we're thinking of as g of x, and the final function. Once we simplify everything down, we have a new function. We have to account for restrictions in that case as well.